Hello, I am Venanzio Giannella from University of Salerno, Italy. I am now going to present you a work in which we investigated the possibility to join together through laser welding additively manufactured parts. We performed mechanical tests at specimen level so as to quantify the strength of the finished products under both static and fatigue loading conditions. At present time, most of the additive manufacturing processes are limited to small-size components, and their joining can be an option to increase the sizes of the finished products. To this aim, we manufactured plates through a laser powder bed fusion machine. Then we joined together these plates through laser beam welding, and then we tested their structural integrity through our laboratory testing machines. The building of the plates was made using a commercial EOSynth M270 machine with its made parameters listed in this slide. The machine operated in full melting mode, which means that the processing parameters were set up so that the powder completely melted during the process. This limited the occurrence of residual porosity, which would instead result when operating in sintering mode. The powder was virgin, thus not used for previous processes, so its flowability required for layering was not affected. These are the plates with related parameters set up for their building. The system for welding comprised a welding head moved by a 6-axis industrial robot. It is worth noting that the standard equipment was upgraded with a protection system preventing the oxidation of the plates. This system was patented in the past and it has been already used successfully for different metal alloys including titanium and Inconel-based alloys. A preliminary optimization process was carried out with the aim of optimizing the welding parameters, power, traveling speed and position of the focus along the thickness of the plates. The key purpose was the overall reduction of defects caused by welding. From this optimization process, a map of the desirability function was derived through a comparison of 27 different weldments. The maximum value of the desirability returned the optimized welding parameters power, speed and focus position. These optimized parameters were then used for the manufacturing of further plates. All the adopted welding parameters are here listed in this table. The welding process was autogeneous, so no filler material was added during the welding. Slices of material were cut out from the welded plates as shown in this picture. Here we can see that the laser welding was performed perpendicularly to the manufacturing direction. These are the main sizes of the final joints, where we highlighted the direction of the slices. These slices were consequently machined so as to obtain specimens for uniaxial static and fatigue tests according to their respective standards. 7 slices were obtained for each of the 2 joints for a total of 14 specimens. These are the different shapes and sizes of the 2 specimen geometries. This one is for the static tests that were carried out on an electromechanical testing machine. By using an extensometer, we derived the stress-strain curves and the main mechanical properties of the specimens. This shape was instead used for the fatigue tests. These were carried out onto a servohydraulic testing machine by considering a piercing wave load and different constant amplitude load depending on the stress level we wanted to reach for each test. All specimens were heat-treated at 650 degrees in vacuum for 1 hour for stress relief. This allowed to enhance the main mechanical properties that were affected by the welding process. As an example, this is a photo of a fatigue test specimen mounted between the grips of the servohydraulic machine. Another specimen is also shown here at right. This is a close-up of the weld bit in the middle of the reduced section of the specimen. Here we can notice the very thin welding line produced by the laser beam. For sake of clarity, the laser beam direction was highlighted in all the pictures. These are the results in terms of stress-strain curves, where we compare the results of these specimens with those of the as-built specimens, then without any weldment. This is a picture of the static failure of a welded specimen, where it can be noticed that the failure occurred sufficiently far from the very narrow welding line. This is a close-up of the fracture surface. The same was also made with respect to an as-built specimen, for which we observed a similar structure. To sum up, it can be stated that, averaging the results among the various specimens, no statistical difference could be noticed at a level of significance of ±2 sigma. Here we can see the results of the fatigue tests. This is a picture of a specimen mounted onto the machine. All the fatigue specimens reported a failure within the heat-affected zone and positioned at the welding toe, as here detailed in this picture for sake of clarity. From the fatigue lives, we built up the Euler diagram shown in this figure at right. We can notice an endurance limit of nearly 270 MPa, that is equal to nearly 55% of the yield strength. We are currently working on making further fatigue tests on the as-built specimens for a comparison with these test data. To conclude, the laser beam welding demonstrated to be suitable to join additively manufactured components, and it presents known advantages to comply with the international standards imposed by several industrial fields, such as automotive or aerospace. Tests reported no strength reduction due to the weldment when we compared the welded to the as-built specimens under quasi-static loading conditions. Fatigue tests reported an endurance limit of nearly 55% of the yield strength. Thank you for your attention.